What we're looking at now is a diaphragm pump. See, it's quite complicated on this side. There's a few extra things sticking out compared to over here. Diaphragm pumps are generally quite small. This one here may be 0.5 meter in height. That's about 1.5 feet if you work in imperial units, although they can be bigger or smaller depending upon the application for which you're going to use them. Let's run through the parts briefly and then I'll show you exactly how it works. There are two things that are flowing through our diaphragm pump. Compressed air is one of them. It's going to flow into and out of the diaphragm pump. It flows into the diaphragm pump through this connection here, and it flows out of the diaphragm pump through this connection where my mouse is now. This particular part is called a muffler. I'll explain to you what it does when we look at how the pump works. The other thing flowing into and out of this pump is the process fluid. The process fluid is going to be drawn in to our suction manifold through this center hole here, and it's going to be discharged via our discharge manifold through this center hole. So process fluid going in and out, compressed air going in and out as well. The compressed air is going to be at around 6, 7 or 8 bar pressure. That's about 80, 90, 100 psi, somewhere around there. That's typically what you'll have for service air. The air that comes out of the compressors is discharged around the industrial plant, or maybe just from a compressor directly to the pump. 6, 7, 8 bar is pretty standard. The compressed air is what drives this pump. It's what causes it to pump. There are, however, other ways to drive the diaphragm pump. You can use an electric motor, and you could even use hydraulics, although this would be quite unusual. Compressed air is the most popular choice for operating a diaphragm pump. The next most popular would be electrical current or electrical power, which requires an electric motor. And after that, if you really wanted to, you could manually operate a diaphragm pump, or finally, you could hydraulically operate a diaphragm pump, although I've never seen this done. I have seen pneumatically operated diaphragm pumps, those that work with compressed air, and electrically operated diaphragm pumps. But as I say, I have not seen hydraulically operated diaphragm pumps, although I'm sure there are a few instances where they exist. When we're talking about process fluid, it could be one of many things. A fluid can be a gas or a liquid or a slurry. It's important to differentiate between liquids and gases. They're both fluids. A slurry is a mixture of solids suspended in a liquid. Diaphragm pumps are good for low flow, low pressure applications. They're also good for pumping fluids that have a low viscosity, a low resistance to flow. Seawater, fresh water, also called sweet water, these liquids have a low resistance to flow. Honey has a high resistance to flow, depending on its temperature, but generally honey is quite sticky, it's quite viscous, it has a high resistance to flow. That would be a fluid that the diaphragm pump is not well suited to pump. Keep that in mind whenever you're looking at a process system. Look at what's being pumped, and then you'll be able to identify what kind of pump is most likely to be used for that application. Diaphragm pumps have other advantages though. They're well suited to operate in corrosive environments. They can pump corrosive fluids because the parts that are exposed to those fluids can be manufactured to be corrosion resistant. They can also be used in explosive or flammable environments. They can be manufactured to be intrinsically safe. That means there's no electrical sparks that come from the pump or any sources of ignition. You can even take a diaphragm pump and partially submerge it in a liquid, or even fully submerge it in a liquid, and it will still work. The only thing you need to make sure of is that if you're using compressed air, the exhaust air coming out of the pump is exhausted above the liquid level. Because diaphragm pumps are positive displacement pumps, they can self-prime. This means they can pump both air and liquid, which means they can pump air out of a system, whereas other types of pump, such as centrifugal pumps, cannot pump air. They're not self-priming. Aside from all of this, diaphragm pumps, compared to other types of pump, tend to have a light weight and they're portable. I've used diaphragm pumps on a number of occasions. you'll pick them up, lug them around the ship or around the plant, drop them off to where you need them, connect the compressed air hoses to the pump, connect the process pipes to the suction and discharge manifolds, and then you can open the compressed air inlet valve and the pump will start to pump. But how exactly is it doing this? Let's have a look at that right now. We'll take a cross section, and now you can see that we've got a good look at all of the internal parts. There's a main air distributor valve. That's this whole assembly where the block is, here where this piston is, and at the opposite end. This valve is sometimes called a distributor valve, center block. There are a few different names for this piece. We have called it an air valve assembly. If I invert the selection, you can actually have a good look at it. Notice there are a lot of seals underneath the air selector valve. Those are important. There are also seals on either of the pistons, indicated in black. We're going to use those seals for restricting the flow of compressed air within this center assembly space. When we talk about the center assembly, or the central part of the pump, we're talking about the space roughly between where these two orange lines are now. The diaphragm pump is called a diaphragm pump because it uses diaphragms. A screw pump uses a screw, a gear pump uses a gear, a diaphragm pump uses a diaphragm. You'll find that this trend for naming a pump after the item that does the pumping is used quite a lot. It's also used for valves as well. If you have a valve that uses a gate as the main disc, plug as the main disc, or a ball as the main disc, the disc is the part of the valve that opens and closes the valve. We name the valves after the discs. We have gate valves, plug valves, ball valves, and various other types. They're all named after the type of disc that's used within the valve. For pumps though, we name the pump after the item that's doing the pumping. We've got two diaphragms in our diaphragm pump, one on the left and one on the right. The diaphragms move from left to right or right to left. They're flexed either outwards away from the center of the pump or inwards towards the center of the pump. The diaphragms themselves are manufactured from a relatively soft material. It's this material that allows them to flex, although if we overflex the material, it may rip and then we'll need to replace it. This also happens when diaphragms become quite old. They sometimes get quite brittle. When you put them back into service, they'll operate for a little bit and then you'll get a tear in the diaphragm, which means the diaphragm can no longer pump any fluid. When the diaphragms move from left to right, they're creating either a vacuum in this space where my mouse is, or a positive pressure. So they're creating a negative pressure or a positive pressure. If the diaphragm moves from left to right, like it's doing now, then that diaphragm is creating a negative pressure within this fluid chamber. This is our process fluid chamber. The process fluid is going to flow in through this suction manifold, so in through this center hole. Then it's going to flow upwards past this little ball, upwards into this chamber. This is our main pumping chamber, or one of them. There's one on the opposite side as well. And then the process fluid is going to flow up again past this other ball and out through the discharge hole via the discharge manifold. This occurs because as we create the negative pressure within this space, we're drawing fluid in from the suction manifold through this little hole, and then when the fluid passes up through that hole, it's going to flow past the underside of this little ball into the chamber, and then what happens is our diaphragm stops moving to the right. It's now going to move to the left. As it does so, it creates a positive pressure within this pumping chamber. This positive pressure does several things. It forces this ball to move downwards, as you can see here. The ball does this a lot quicker than what's just been shown, and when that ball has seated, it blocks off the hole. That allows the positive pressure to build up within our pumping chamber. You can see the diaphragm's now quite extended. It's gone into the pumping chamber. And because of this, the positive pressure has lifted up the other ball. It's been lifted off its seat, and then the process fluid flows through this gap into the discharge manifold, and then along here and out of the pump. Now, if we go back, our diaphragm is going to gradually move to the right again. We're creating a negative pressure which draws this ball off its seat, allows process fluid into the pumping chamber, whilst at the same time we're going to draw this ball down onto its seat, and we close off this upper chamber. So when we're drawing the process fluid into the pumping chamber, the lower ball is sucked off its seat and the upper ball is pressed down onto its seat. When we're pumping out of the chamber, when the diaphragm is expanding into the pumping chamber, the upper ball is lifted off its seat by the positive pressure and the lower ball is pressed down onto its seat by the positive pressure. Thus, the lower ball closes off the flow so that there can't be any backflow through the pump, and the upper ball allows flow from the pumping chamber into the discharge manifold. These balls and the seats that they sit upon, and also this retaining piece that prevents the ball from just floating away through our discharge manifold, those three items create a non-return valve. Sometimes the ball will also have a spring on it, sometimes not. It depends upon the design. The spring is used to really press the ball against its seat. I mentioned that these three items form a non-return valve. The ball is the disc of the valve. This lower piece where the ball sits is the valve seat, and the other piece is a retainer. I suppose you could call it the body. It's called a non-return valve because we only allow flow in one direction. We don't allow the flow to return. So flow is only ever going to be from the lower side of the pump, from the pumping chamber, up and into the discharge manifold. There's no return flow allowed. It's a non-return valve. Non-return valves are also sometimes called one-way valves. They're also sometimes called check valves. I think they have about 4 or 5 different names, but all of those names mean the same thing. If you want to use any of the 3D models shown in this video, then head on over to savry.com. We've got over 400 engineering 3D models that you can use directly through a web browser in AR or VR. If you want to learn more about engineering, we've got over 45 hours of engineering video tutorials and courses at savry.com, and you can learn about valves, pumps, power stations, electrical transformers, and many other common engineering machines and processes. Before you go, don't forget to subscribe to the YouTube channel. Thank you very much for your time.